안녕하세요. 학생 여러분. 제가 뭐 영어로 떠들다 보니까 이 벡터 캘큘러스 그 동영상 시청률이 매우 저조합니다. 사실. 이제 저도 뭐 사실 영어로 하다 보니까 되게 버벅대는 게 많고요. 나름 그 저기 강의 자체 내용도 이렇게 뭐 쉬운 내용은 아니기 때문에 그것을 이제 영어로 긴 시간 동안 설명을 하려다 보니까 조금 그 제 자신이 굉장히 부족함을 많이 느꼈습니다. 그럼에도 불구하고 또 유종의 미를 거두기 위해서 저는 저 나름대로 또 강의를 또 끝내야 되니까요. 그래서 오늘 마지막 시간 이제 내용 정리하면서 끝을 낼까 합니다. 특별히 우리가 피직스에서 이제 그 다루는 일렉트로마그네틱 시오리를 살펴보고 있는데 제가 아는 지식이 요 정도밖에 안 돼서 그 응용으로서 이제 맥스웰 방정식을 살펴보는데요. 뭐 그 외에 여러 가지 공학 분야에서 또 스톡스 정리라든지 그 가우스 정리 같은 거를 쓰는 분야가 있으면은 뭐 혹시나 여러분들이 아시면 저한테 알려주시면 저도 감사를 학생들한테 또 배우는 게 있을 것 같아요. 하여튼 긴 시간 동안 강의를 경청해 주신 또 학생 여러분도 계실 테니까 감사 인사는 한국말로 우선 전해드리고 싶어요. 일단 시험은 뭐 별개로 여러분들이 또 강의를 통해서 이 모든 학문들의 내용이 사실은 수학의 기본적인 어떤 것이다. 그리고 수학으로 설명할 수 있으면 그 이론은 완벽하다고 우리가 보통 이야기를 합니다. 그래서 이제 전자기 이론은 이미 수학적으로 완벽하게 이제 표현이 됐기 때문에 확실히 확립된 이론으로서 이제 우리가 많이 응용을 하고 있고 그러다 보니까 이제 실생활에서 여러분들이 이 전자기파를 이용한 통신, 그죠? 우리 인터넷이라든지 그리고 전화 사용 같은 거요. 이런 것들을 할 수가 있는 기본적인 근간이 되는 것이죠. 그래서 예. 그래서 마지막 강의를 시작하겠습니다. So I now speak in English. Okay, now we let's pack up the what we observed for a long time. So we actually start with the static theory about the Coulomb potential. I mean, actually, when you have a point charge or multiple point charges, then we could define this Coulomb potential. From Coulomb potential, we know that electric field is given by the gradient of the Coulomb potential. Okay, so remember that, and then we were able to show that this total charge can be computed by the electric flux of the electric field through the surface, okay, which enclosing the point charge. So, in such a way that we electric field actually we assume that there's no time change. I mean, there is no magnetic field presence. Then we were able to say that the electric field is coming from the point charge only. Then in that case, so that the electric field has an electric potential. Okay, so that's the another story, and then when time varying magnetic field is present, then the last time we observed that, so the magnetic field itself could have a vector potential, right? Vector potential, so called as we denoted the vector potential by A. Okay, so I mean from this magnetic monopole theory that you see the divergence of the magnetic field was zero, right? So remember that gradient dot B was zero. So that's a magnetic monopole. In that case, we could assume that this magnetic field has the vector potential. Okay, so then we know that there's vector potential, and then the magnetic field is time changing. Time changing case that electric potential is no more possible. So electric field also affected by the magnetic force. So their interaction is somehow complicated. Then we now want to we actually derive the something so-called this Ampere-Maxwell equations, right? So remember that the Ampere-Maxwell equations. So let's come back to the iPad. All right. So here that so if you multiply this. So last time we derived that this curve of B is not just a J, but instead of J, we must have this curve of B is this form, right? This mu 0 J plus mu 0 times time change of this electric field, right? So that's Ampere's Maxwell equations. So we are going to use this this equation 13 again, but this time we want to explain the Faraday's law. Okay, the Faraday's law. So now let's look at the iPad. So this Faraday's law about this when you make the time change of the magnetic flux, then this magnetic flux induces the current along the ion ring. So we were able to detect the current through the ion ring. Okay, and such current is we think that this electric force actually move the charged particle or electrons through this ring. So this is the work done by electric field. Okay, so which was induced from magnetic field. Okay, so this is not the electric field we have seen in the Gauss law. Okay, this is different. So this is different in the sense that this is induced electric field. Okay, so I emphasize again that this electric field is not the same as the one in this Gauss law. Okay, so the Gauss law case, we say that that's static electric field. Now it's because of the time varying magnetic field presence. That presence actually induces the current. So it induces the current, so it induced the electric field. Okay, so now so the experiment itself shows here the picture that when you move so here that when you move the mechanism here, then this mechanism itself has the you see this magnetic flux. But this magnetic flux is if the mechanism is stopped, as a time is not time changing, that magnetic flux has no time change, right? But when you move it, then the flux gets strong, right? So the flux gets strong, and there is time change. So the flux has the time change. Now, then he observed that there was a current, right? There was a current observed. So we say that the time change of the magnetic flux is is equal to the this current. Okay, so they're equal to the current. So then this current actually is the energy which is done by the induced electric force. So what's the flux of this because of this magnetic field? So we say that this pi sub b as the flux of this magnetic field throughout this surface S. Okay, so here is the surface S, and this is the boundary, as it would say C. Then so this is the usual this you see the surface integral of the vector field is the flux here. Now, then as a time change means that we just take the time derivative, right? So this time derivative, so we say that this time derivative is that partial b over partial t. Okay, so this is equal to what? This is equal to the minus energy, which is, I mean, so this is minus electric field, which is induced one. This is induced one dot dr, which is the line integral of this vector field, right? This is the energy was computed by the field was just a line integral along the path, right? So this is the path is the C right here. So this is the Faraday's law. All right, so this is the Faraday's law. So then let's come back to the PDF file now. So look at that. So this is so this one is the flux of B throughout S. But then I said that this is equal to this time change of this flux is equal to the work done by electric field, induced electric field. So so then you see. So in the left hand side, then we have the integral of this vector b. I mean, the left hand side is the surface integral of this vector field b throughout the S. But then we just get into we can move this time derivative inside of the integral here, because and then you see this is the right hand side that was equal to the minus E dot dr. But if you apply the Stokes theorem, so that the Stokes theorem means that this line integral coming from, because of C is closed, right? And which is the boundary of the surface S. So in that case, that this boundary is interchanged with this curve. So we actually this line integral is actually the curl of something, or the surface integral of the curl E, right? So this is in the second line to the from second line to the third line. This is we apply the Stokes theorem. So now we have this curl of E of the in the surface integral. So this the first one and the second one is equal. So now we have that this curl of E is not zero, right? I mean, so if E has the scalar potential like Coulomb potential in the previous case, when we have the Gauss law. But then now, if that was the case, then curl of E must be zero, right? But this curl of E is not zero. This is just the time-varying magnetic field present. So this the time derivative of the magnetic field is not zero. Okay, so if it were zero, then there is no time change. So then this curl of E is 0, so that's the curl of E is just the electrostatic a static case, so it could have this electric potential, scalar potential, right? So there's everything is well combined together. Now we have this Paradise law. We express this Paradise law by differential equation of this form, this equation 14. So this curl of E equal to minus this time derivative of this magnetic field. So this shows that electric field and magnetic field in the time-varying change situations that there are interaction. Their interaction is now captured by these equations. Okay, so this is the last equation of the Maxwell equations. So so now let's come back to the let's come back to the iPad and observe that consequences of the Maxwell equations. Okay, so as I emphasize that, so when let's again this look at what's the consequences of the Maxwell equations. So if you remember this Gauss law of the Coulomb potential case, that nabla.E is a total charge, right? So this is the divergence of E is the total charge, something, the charge density. So that was the first Gauss law of electricity. And now when the time-varying magnetic field presence, which induced from E, that is induced from this magnetic time-varying magnetic field, then E is no more conservative. Okay, so this conservative means that there was a several equivalent conditions about this whether this given vector field is conservative or not. The first, then we actually whenever we have a closed line integral of the conservative vector field, then we were able to evaluate that line integral by the scalar potential evaluated at endpoints, right? So if it was a conservative, if it were conservative, that means that whenever we have a closed curve and line integral about that closed curve, then the consequence is always 0, right? If it were the conservative. So that was one condition we can check. And the other condition was that we can compute the curl of the E. So by the Poincaré's observation that if you compute the curl of this vector field, the curl of that vector field is 0, then we can actually cover that this is conservative, right? So that was the by Poincaré. So that's very important. So by those two consequences, I mean, if you remember that this last equations that gradient of this the curl of this electric field is minus a time derivative of this magnetic field. So this is not 0, so the curl of E is not 0, so the curl of E, so that means that E is no more conservative, right? So that we emphasize that point. And even though this this induced electric field is not a conservative, but we can still seek this the conservative vector field. Okay, so so look at that. This E, the induced vector field E plus, you see this curl of the B is divergence of B. If you remember this non-magnetic monopole case, that this divergence of B is 0 means that this B has a vector potential. So then let's say vector potential A. So then if you combine this induced electric field plus the this time change of this vector potential, say that this is the both are vector fields. So let's say f equal to the e plus partial a partial t. Now this is new field. Then we claim that this is conservative now. Okay, so why is that conservative? As I said, that we can actually check that the closed integral condition, but rather closed integral condition by the Poincare observation that we just compute the call of f, right? So here we compute the call of f. So nabla times f. So we apply the nabla times in both sides, and here we have a nabla times e plus nabla times partial a partial t. So we can actually, so the a, but if you remember that we can actually, these two operations, the time derivative and the nabla times, and the call and time derivatives are commutative. So we can actually switch this order of these things, and so we actually switch the here that this nabla over nabla time, this time derivative is later, but we apply the nabla times first, nabla times a for the first, and nabla times a equal to the b by the definition, right? It's the definition of the vector potential. So it's equal to the b, but if you remember the last time, last equation of the Maxwell equations, that this Faraday's law, that this electric field, curl of electric field is not zero, but it's the time derivative of the magnetic field, right? So this is equal to nabla b over nabla t, and then a partial b over partial t. So if you combine this the second term, then this first term and the second term cancels out, it's zero, right? So by this point that we have this nabla times f equal to 0. So that by Poincare's lemma, that this f is conservative. So this means that f has some scalar potential. So let's say that b sub f as a scalar potential for a vector field f. Okay, then you see that you see this. So this f is. In other words, that f is just the gradient of the bf's, right? So this is the what's the scalar potential. Now we replace by this f by nabla of the bf here. Then the right hand side was the just by the definition, that's the induced electric field plus the time varying electric field plus the in this case that we have a x comma t. So we have the in this case that this is time changing. So this time space is our domain. Okay. So in previous case that when you consider this Coulomb potential case, that we didn't consider the time variable. So, but now we also include the time barrier as a domain. So right, so that this so it's okay now. And then this time space actually coming from this Einstein's special relativity law. So special relativity says that there is no subject which is the faster than light speed, right? So that's the special relativity. So if you consider such special relativity, then it turns out that this electromagnetic theory of this Maxwell equations is not contradictory to the special relativity. Okay, so this theory is the in that sense very important. So all the physics are combined, and so 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 this is very meaningful in some sense. So anyway, so we say that we found that this electric field still has a potential, some scalar potential, but considering the time effect of this magnetic field, right? So if the vector potential is time invariant, which means that this is zero, then we have a really this time about the time. This E is no, we don't have to consider the time t variable. So in that case, it's come back to the Coulomb potential case, a static theory, that we just have the scalar potential, and in this going to be Coulomb potential as we observed, right? So so now everything just you see is well established for even for time varying magnetic field presence. So this is the consequence, and then if you study the quantum mechanics in physics department, then you may learn how to calculate or how to solve Maxwell equations. Okay, so but in this elementary course, that I mean both reasons. One reason is that our mathematics students and is not acquainted with this physics laws, and secondly, actually, it's not easy to find the solutions of the Maxwell equations, and so it requires deeper knowledge about this differential equations further. I mean, we need to study that the partial differential equations about, especially wave equations. So such a case that you need to take the advanced course for solving the differential equations. Okay, so this is not ordinary equations, but we just have the four variables in time and the space variable, right? In the four-dimensional space, and if you learn further this Lorentz transformations, which is the not Galilean transformation, that if you consider special relativity, then you need to introduce a special inner product in the time space, four-dimensional space. If you know that there's linear algebra, then you know that there is a canonical dot product things and the measures of the vectors, but in special relativity, if you consider the special relativity, then you need to introduce the Lorentz transformations or Lorentz metrics in time space, and so in that case, I mean, in math students, in terms of the math students case, that they need to learn this differential geometry further. So anyway, so to solve the Maxwell equations, that you need more, right? You need more. So and you need to study more carefully partial differential equations and differential geometry. I mean, so although those Lorentz transformation is not that very difficult, but anyway, here we just packing up things, and I mean, just remember that in several processes that we apply the Stokes theorem and divergence theorem to get these differential equations, right? So hopefully, I mean, again, I want to also say something about this, that this mathematics could be beautiful in your point of view, but this modern language of this field theory is is a little bit shifted. So people just rather looking at the vector field itself, I mean force, but people just are more focused on the potential thing, right? I mean vector potential, or this magnetic vector potential, or this scalar potential, right? So this potential is more important than the field itself. So I want to say this message, and yeah, it's time to say goodbye. Okay, so I hope you to have the good luck in your final exams. Okay, uh, thank you for watching.